Yeah, so I'm going to talk a little bit about our project, which is not focused on marine cloud brightening, which is a lot of what I do work on, but using some of the ideas and some of the concepts techniques that we've been employing for looking at plume spreading in the boundary layer and applying that to the stratospheric aerosol injection problem in general. So the team consists of two organizations, University of Washington and Sandia National Laboratories. We have all the team members here except for Lekha Patel, who's unfortunately had to attend some other meeting this week. So everyone's here. I won't go through them, but you'll see, you're going to meet them this week. And so I'll talk about different pieces of work that individuals have done as we move forward. So the basic outline here is we really want to know, if we want to understand the effectiveness of any stratospheric aerosol injection or any intervention in general, we kind of need the GCMs to do that. If we want to know impacts or if we want to know how much material we need to put in, ultimately you need to go through the GCMs. The GCMs resolve certain scales. You can see typically pretty coarse resolution, but that's good for a lot of things. What it's not maybe good for is thinking about what happens when you first inject particles into the stratosphere. And that might be, in our project, we're kind of being somewhat agnostic to the approach. That could be, for example, is it a very, very fast-moving platform, which it would presumably be if it was aircraft injecting particles. Could be a slow-moving platform if balloons or some other method was employed. It could also be different materials, right? So it could be gases, it could be particles. And so we're kind of trying to remain agnostic to that so we can kind of, really what we care about is the dispersion of the particles initially, because that sets a lot of the process rates that may be non-linear and why you need to understand how you go from the small scales up to the larger scales. And so most of what we're doing so far is really looking at these small-scale processes that set this natural turbulence in the stratosphere and what causes plume spreading, how fast will that plume spreading be, what might be the consequences be for coagulation. So this morning Karma was mentioned, Simone mentioned Karma and box models. We could do a similar thing, but in a plume, right? In an expanding and diluting plume, we could put our box model into that and look at that would be an additional level of realism in there compared to a box model where you fix the size of the box. We could have a diluting box, for example. So there's a lot we can do with that. This would involve things like large eddy simulations, looking at observations, getting it all the way to learn behaviors from that we can put into a kind of a larger plume model that then could be inserted into a GCM. So that could be like a pluming grid model, for example. So our first focus is kind of assessing what we know about turbulence in the stratosphere, ultimately wanting to derive things like diffusion constants that can be then put into and maybe understand how that these are not constant and they're variable, and how can we incorporate those in to models that can be then used to kind of do plume spreading at the GCM scale, and looking at vertical wind shear as well, which turns out to be very important for plume spreading. So there's kind of four different pieces to this work. I'll touch on large eddy simulation, which is one approach to actually explicitly modeling the turbulence in certain regimes in the stratosphere, and I'll also highlight why that's really difficult to do under many circumstances, in contrast to the boundary layer. We have a Langevin particle model. This is a particle model that follows a turbulence theory by Pope that goes beyond the level of just Brownian diffusion and can represent memory in the system, velocity memory. And so you can get plume spreading that's a little bit more complicated and sensitive to input parameters than you might get out of a simple diffusion model. So this is just, the figures there are from marine cloud brightening work, but it's showing the width of the plume as a function of time. And so what you can see is that the plumes do not necessarily just broaden and then slow down with time, but actually can speed up again, because in this model, there's actually cloud processes that are driving the spreading rates. So we can feed that with information either from a large eddy simulation, as I'll talk about, or from observations directly. So that's another approach. A third approach would be to use a kind of a Lagrangian trajectory model. I'll talk a little bit about that later. And another technique that we're going to kind of employ is, and this is getting a little bit outside of the stratosphere, but it's acknowledging that this project also has cirrus cloud thinning and marine and mixed phase, and also seeing some similarities between what goes on in the upper troposphere and what goes on in the lower stratosphere. You know, the contrails may be a useful metric for looking at the initial plume spreading by natural turbulence under different scenarios. And so we're thinking about using those. There's a big database that Sandia have put together, for example, that we could probably employ for this to look at plume spreading rates, sort of empirically. So large eddy simulations, basically this is, our plumes are spreading because of turbulent motions, but our plumes are also spreading laterally by shear. And shear in the stratosphere, because it's a relatively intermittent turbulence regime, shear can get very, very strong in the stratosphere. And so shear is not necessarily mixing, but it does change the dimension of the plume, and it changes its surface. So if you think about a spherical core plume and you spread it out, you've got a lot more surface area to that plume. So then when turbulence acts on it, it can mix it out faster. So shear itself does not necessarily dilute the plume, but it makes it more amenable to later dilution. And so that's something you can do in the large eddy simulation model, which is representing the large, the energy-containing eddies in turbulent flows. This is going to be a little bit, we're going to probably use the LES to look at turbulence in certain sort of intermittent regimes where there's gravity wave breaking in the stratosphere, where you get turbulence a little bit stronger and more amenable to large eddy simulation. Stratified intermittent turbulence is very tricky. It requires very high resolution, but then if you imagine 1 meter per second of lateral shear in a plume, that in a day goes 100 kilometers. So you need a very big domain at the same time as you need very high resolution. So it's really not suitable for a lot of the work, but is suitable for certain cases, wave break. And this is just showing you a boundary layer simulation where we have a plume coming in and looking at different times, and we can look at the evolution of the plume over time. And then using that, we can we explicitly resolve the turbulence. We can use those turbulence parameters to drive Langevin particle model. In this case, we're not driving it with LES. We are doing that in the boundary layer. This is just a model that can basically represent a little bit more complexity of the plume spreading. So this is an example where aircraft is flying through, and we're taking the observational the turbulence parameters, which is basically velocity variances, turbulent scale velocity variances, and a dissipation rate, turbulent dissipation rate from observational data, in this case ACLIP, which is a WB-57 NASA aircraft flight. We're just using stratospheric part of that to learn the dissipation rate and the relaxation timescale that feature in this particle model. And then what we do is, it's a stochastic model. It's basically introducing super droplet, if you want, a super particle method. Each of those particles is sort of representative of a whole host of particles. So you have these representative particles, and you can look at the spreading rates in this case, right? So we've been taking in a lot of aircraft observations of existing data from the stratosphere to try and understand those parameters and how variable they are, for example. One of the things, oh no, this is this one. So one of the things we are finding is that in the stratosphere, the drift term, which allows gives a bit, you can have linear spreading rates, more linear-like, and give rise to the more complex spreading, as opposed to just a square root spreading, which is kind of Brownian diffusion. We're finding that actually Brownian diffusion is pretty good for these low turbulence levels in the stratosphere, at least so far. And so it's actually kind of simpler than we may have thought, but this is just one case, so we need to really explore that. And the idea is to take data from a number of different platforms and see, hey, if we force the model over and over again with different turbulence amounts, it's a matter of getting good statistics. Will we be able to get spreading rates that do different things than just a square root growth? I'm going to skip the rest of the stuff on this slide, I think. So this one way we do find that you can, at least in terms of looking at aerial coverage, is vertical wind shear can be very strong. This top simulation and both of them have introduced a couple of blobs of material at different levels, and there's a shear between them. And you can see, so both of them are spreading with this kind of quasi-square root law, but they're also spreading laterally, and it ends up with spreading rates that kind of end up more linear with time. So we've got an aircraft simulation in here, but there's also at the bottom is a balloon simulation, and you can see that those two, the bottom one and the top one, have become dissociated from each other. So this is how contrails probably most effectively spread. And so this is going to be quite important, because when the spreading occurs, those layers are getting thinner and thinner. You don't see that from a top-down view, but that's quite important. This is to say, why are we doing this? Well, one of the reasons we're doing this is because the processes in plumes, coagulation, for example, depends on the square of the concentration of particles in there, because one thing has to collide with another, so it depends on the probability squared of the existence. And so that means that you're very nonlinear aggregation, right? If you have a plume that's narrow versus dilute, you get very different process rates for aggregating. The aggregation will go down. Calling it aggregation, but it's the coagulation, I guess, is the more common term. But the coagulation of the particles really is very sensitive to the concentration, and if you can dilute that, the faster you can dilute it, the less agglomeration you'll get. So this is where we need to know the plume spreading rates and the dilution rates to get the right aggregation rates. And so this is just showing a microphysical scheme that we're going to be using, which is this piecewise log normal approximation. We could use this, we could use the Karma model. This is to get at the processes within the plume. And there are other processes that are not coagulation that are probably also nonlinear. The chemical process rates might also be nonlinear. Heating rates of the plume, if there's absorbing aerosol in there, might also be nonlinear. Don't know about that one. The third method is using the Lagrangian trajectory to estimate diffusion. So this is where you have a chemical transport model. Maybe you're representing, in this case, ozone. This is showing ozone as a function of potential temperature. The chemical transport model is the red. And the idea here is that you take each point and you do back trajectories. For each profile, you do back trajectories, and you aggregate together what you take the chemical transport model predictions of ozone at different points, and then look at dynamical trajectories going back that end up at the point you're looking at, which is the observed profile, making assumptions about how diffusive the motions are, which is basically going to add turbulence noise to each of those. And you see how do you get a different profile, how noisy is the profile. That depends upon the assumed diffusion. And the idea is you try and select a diffusivity that kind of gives you a match with the observations. So we haven't done, this is not our own work, this is from a paper quite a while ago. So, but this is something we may think about employing here as well. Finally, exploring plume spreading from satellite. So this is, again, the idea of using contrail observations, upper tropospheric clouds made by aircraft, and which occur frequently. We can look at them in long-wave imagery or even in short-wave satellite imagery, and then potentially derive spreading rates, knowing the width, and knowing something about the speed of the aircraft or the speed of the winds. You can figure out. The idea is you can figure out spreading rates. They may actually be quite slow, but we could look at that under different conditions, different environmental conditions. There's another way to get at the diversity of how the plumes respond to different meteorological conditions. All right, so that's basically where we are now. We've got these different thrusts areas that we're kind of focusing on, and we're bringing all those together. We really like to collaborate with other groups. The Karma was an example. The next talk here, where they're going to be looking at aircraft wake turbulence. We're really not trying to do that. We're trying to look at the natural turbulence that would occur once that wake's effect has petered out. So there's some real potential for collaboration there, and particularly looking at the materials different materials and different chemical processes, aggregation, for example. Yeah, what can we learn from that by combining this plume spreading with a microphysics model? Yeah. So I'll leave it there for now, but thanks.